Have you ever wondered why, when you drop an object, it falls faster and faster? Or why objects follow a parabolic path when you throw them? Well, in today's video, I'll be answering those questions and explain kinematics to you. Let's dive right in. Let's begin with the basics about movement, URM and UARM. When an object moves at a constant speed, we say it performs a uniform rectilinear motion, abbreviated as URM. If the object moves with a constant velocity, it covers the same displacement in meters during equal time intervals in seconds. The Greek letter delta represents a change in a quantity. In this case, it represents the change in time and the change in position. From this, we can derive the formula for velocity. Velocity equals change in position divided by change in time. When the velocity is positive, the motion is along the positive side of the x-axis. When the velocity is negative, the motion is along the negative side of the x-axis. This is an important distinction to keep in mind. The position versus time graph of a URM, written as x of t, is a straight line. The position at a given time is given by x of t equals velocity times time plus initial position. The velocity versus time graph is a horizontal line, given by velocity of t equals velocity. This line represents the slope of the position graph x of t. Look at this example. The light blue line, y is equal to 1/2, is the derivative of the dark blue line with a slope of 1/2. It's important that you know this because this will be very helpful later on. Notice that you cannot determine the initial position of the object from the velocity graph. You can only determine its velocity. Also, the area under the velocity graph corresponds to the distance traveled by the object. For example, if we have an object with a velocity of 2 meters per second, then we can calculate the distance it moved in 10 seconds, both algebraically and visually using the graph. Algebraically, we can rewrite the formula. Velocity equals delta x over delta t. So delta x is equal to delta t times velocity. Then we get that delta x is equal to 2 times 10, which equals 20. Now visually, we have the horizontal function y equals 2. We can mark a rectangle with a base of 10 like this. Then we can just use the formula for the area of a rectangle, which is base times height. So we have a base of 10 times a height of 2, which also equals 20. This can be very handy sometimes. If an object does not move with a constant velocity, but it is accelerating or decelerating, we say it performs a uniformly accelerated rectilinear motion, abbreviated as UARM. The graph of the velocity won't be a horizontal line anymore, but actually a line with a slope that is non-zero. Because the object is accelerating or decelerating, we can't use the formula v equals delta x over delta t anymore. It's important to know that you can only use that formula when you have an object with a constant velocity. Since the object doesn't have a constant velocity, we can calculate the average velocity on a time interval using the same formula. But there is a twist. Average velocity equals change in position divided by change in time. So we calculate the average velocity on a time interval and not the exact velocity. Look at these two examples. Both graphs show an x of t graph with a URM. The top one shows an average velocity on a time interval, and the bottom one shows the exact velocity of 2 points, A and B. Again, we will be able to calculate the exact velocity by deriving the function rule, but that's for later in the video. When acceleration or deceleration occurs, we can also calculate the average acceleration, which we denote by A. The average acceleration equals change in velocity divided by change in time. This is very similar to this formula. The unit of acceleration is meters per second squared, and the graph of the acceleration is a horizontal constant. So because it is a horizontal constant, we can say that the average acceleration is actually equal to the exact acceleration in any given point. The acceleration will always be one number. Let's look at combinations of velocity and acceleration. If the velocity is positive, the object moves to the right. If the velocity is negative, the object moves to the left. But what happens when you also have an acceleration? If the acceleration has the same sign as the velocity, the object accelerates. The object either moves faster and faster to the right, or it moves faster and faster to the left. If the acceleration has the opposite sign of the velocity, the object decelerates. It either decelerates to the right or decelerates to the left. This is crucial for solving problems. Just like with URM, we can also draw graphs for UARM like I showed you when I was explaining the difference between average and instantaneous velocity. The position versus time graph, x of t, has the shape of a parabola since it follows a second-degree function. The formula is x of t, which is the position at time t, equals 1/2 times acceleration times time squared, plus initial velocity times time, plus initial position. Any of these values can be 0, and if the acceleration is 0, the formula simplifies to that of URM, which makes sense because the velocity is constant when you have no acceleration. The velocity versus time graph is a straight line, given by velocity at time t equals acceleration times time plus initial velocity. From this graph, you cannot determine the initial position, but you can identify the initial velocity, which is v0. The acceleration versus time graph, like you saw 2 minutes ago, is a horizontal line given by a of t equals a. If you have a URM, the acceleration will always be one value, and thus it will always be a horizontal line. Understanding these formulas about URM and UARM allows you to solve almost any problem involving motion. So, write these down because they're very important. Finally, I want to talk about gravity and vertical movement. Horizontal movement is for another video. As you may or may not know, gravity is similar to acceleration. The only difference is that the gravitational constant on Earth is always 9.81 meters per second squared. But this can differ a little bit depending on where you live. When you're solving problems, you can just use the same formulas we saw for URM. Just replace the a with minus g. But why do we use minus g and not just g? Well, when we look at gravity, it pulls you down, so the x of t graph will decrease until you hit the x-axis, or in other words, the ground. The only way a parabola will decrease on the right side of vertex of the parabola is when the highest degree term is negative. That's why we use minus g in our formulas and not just g. When you want to find the sign of the velocity, in other words, when you want to know if the velocity is positive or negative, for example, if you throw something up or down, look at the direction of the vector of the velocity. When the direction of the velocity vector is up, you use a plus sign, and when you throw something down, you use a minus sign. I hope you enjoyed the video. If you like this new style of videos, leave it down in the comments. I would appreciate it if you would like and subscribe to the channel. Thanks for watching. Bye.